Well, hello everyone, and thank you for joining today's Fastcast, Maximizing Water Tower ROI, Optimizing Cooling, Decrease Cost. This is Vincenzo Cutrone, Marketing Manager for Watersan and Evoca brand, and I'll be your moderator. Our presenter today is Keith Carl. Keith Carl, HVAC filtration expert with over 30 years of experience consulting water treatment operators. Keith has helped various Evoca customers design a complete filtration system that meets today's challenges and tomorrow's goal. After the conclusion of Keith's formal presentation, we'll have a live question and answer session. Please submit your questions at any time by typing them into the Q&A panel on the right-hand side of your screen, and be sure to send your questions to all panelists found within the drop-down menu above the text box. Keith will be answering as many questions as time permits, and will follow up offline with any questions that we did not have time to address during the live event today. And now I'll turn it over to Keith.
Good morning, and thank you all for attending today's presentation. Some of the things that we want to talk about today is first understanding suspended solids, the impact that they have on all of your equipment, whether it be your cooling towers, your chillers, your heat exchangers. Suspended solids play a vital role in diminishing efficiencies today. When you look at micron-sized particles, typically 5-micron particles will start to adhere to surfaces first, followed by finer micron particles after that. So once we have an opportunity to show you the importance of being able to remove the very fine microscopic suspended solids, I think you'll see exactly where we're coming from. You want to be able to optimize your equipment, reduce your risk assessments for subjects like Legionella, which are every day in the news, and reduce the biofoul potential of the system. So let's take a look at you look at these beakers with the the big circles in it. That represents like a 1/2-inch diameter of chip scale, iron scale, whatever it might be. Now, if you were to take that 1/2-inch piece of dirt and break that up into 2-micron particles, you would have 256 billion 2-micron particles. What do you think is the hardest to get out? Not the big stuff. Strainers and things of that nature will remove that very easily. The difficult suspended solids are the fine microscopic solids under 5 micron. Over the last 15+ years, we've been conducting particle distribution on all cooling waters, and we know that 85% of all the circulating dirt that's in a cooling tower system will be under 5 micron in size. So when you look at other technologies, which we're going to review the popular type of technologies used today, but when you look at how they size their products, when you look at a particle distribution analysis, they're always leading it over to the mass bin or the volume percentage, which is the big particles. And they can state 90% removal by weight or volume of whatever micron size particle that is. But it has to be very, very heavy and very large in order for certain technologies to remove. So, if you looked at that 1/2-inch diameter piece of dirt and that equaled 1 ppm, well, so does 256 billion 2-micron particles. It's still the same. So when you look at a particle distribution, we're always looking at the other side of the equation, which is the volume of fine suspended solids. You will find today, because chemistries are very enhanced, you'll see that there's dispersants that they use, and that keeps the dirt broken up into the real fine microscopic range. So some of the things that filtration can help avoid, are erosion in the piping, valves, mechanical seals, impellers, heat exchangers. You look at all the other aspects, the dirtier the water, the more difficult it is for the chemical treatment program to be fully enhanced. If you have very dirty, turbid water, the chemistry is going to be absorbed and be less effective. So removing those suspended solids becomes vitally important to be able and combine a really good chemical treatment system with a very good high efficiency filtration system. They work hand in hand. The other aspects, again, are biologicals. When you look at a cooling tower and how it operates, you have low flow velocity areas where you're going to get an agglomeration of those real fine particles that circulate through the system. When they hit those low volume areas, like a cooling tower sump, they will agglomerate, thus creating a sludge buildup in there. Well, the chemistry can't penetrate that sludge. And the same thing if you look at a chiller and you look at your condenser chiller tubes, and any settling of suspended solids that occur there, if they don't get removed, then what happens? You'll get microbial induced corrosion. You'll get all sorts of things going on, and you'll also be able to harbor biologicals. So what we want to do with fine filtration is be able to decrease the amount of cleanings that you have to do. You'll never eliminate having to clean a cooling tower 100%. It's just a fact of life. Even with the best sweep piping arrangements, you'll never get it all out of there. So, again, we want to reiterate this. The fine particles are what adhere first, followed by the finer particles after that. When you look at control valves, they'll get dirty. They'll start to fail. You look at the piping diameters as they decrease and velocity changes. You'll get coil and heat exchanger fouling and plugging. These are the things that cost your facility a lot of money. And the other aspect today that we all read about with Legionella, and what the cost of that would be if it ever got out of control for you. So understand that that needs a food source, and fine suspended solids are what give it its food source. Now, when we look at heat transfers, and different materials, as you can see, have a different conductivity. And when you look at biofilm, also known as biofouling, that material, it does not have to be as thick as some of the other elements to create as much as 4 times the insulating factor, say like, calcium carbonate scale. So you need a very thin layer in order to start driving up your energy costs. And there's a table on the left side that kind of gives you a pretty good percentage increase in energy. Because let's just say you had a 500-ton cooling tower, and the chiller companies have a certain fouling factor built into their design for optimum efficiency. But as soon as you start to put any kind of film on those chiller tubes, you will not get the heat transfer. So when that happens, your tonnage goes down while you're trying to maintain a certain water temperature, as your energy costs start to skyrocket. You can see also there's an illustration on the right. That happens to be a cutaway of cooling tower fill. And basically with cooling towers, they're a great filter. The one problem they have, they cannot backwash themselves. So you can't really see inside the fill packs, but that's where you start to get a buildup of the fine suspended solids, and it just keeps packing in there and packing in. And what happens is you decrease your efficiency on your cooling process through your cooling tower. Here's an example of a client that we did. On the left, you can see what type of sludge buildup there was in their cooling tower before the installation of a high efficiency filter. And then there's a picture a year later where they didn't have to go in and pretty much clean anything. So we're going to review the efficiencies of high efficiency filtration and what makes this happen. All right, so some of the key things and trends today, is water reuse, the green initiatives. Our technology was the first, green certified product in North America. We've won some projects on rainwater reclamation where we had lead points also attributed to the high efficiency filtration. But you have to consider, like, cooling towers are your #1 culprit for suspended solids because a cooling tower sweeps the air of all fine suspended solids. So aside from what's happening internally with your chemistry, keeping your biologicals in check, you're going to have dead and living biologicals in there, but they're under control. You're going to have, like in a chill water loop, if it's a real tight system, yeah, it's easier to control because you slug feed your chemistry. But if it's a leaky system, you introduce more potable water in there for makeup, which tends to bring in more oxygen and will lend itself to corrosion. What you also find in some of these closed loops is some iron-fixing bacteria and sulfur-reducing bacteria as well. And they could be very, very detrimental, not only to equipment, but to people. You look at data centers. Data centers are mission critical, and they're typically built with a lot of redundancy. But their need for water savings and clean water and energy savings is at the highest level. The same with semiconductor type of applications where you need to have super good quality water followed by, ultra pure water systems. So we can remove a lot of the suspended solid debris before it gets to the very expensive RO membranes. So, we want to look at improving all of your cooling efficiencies. High efficiency filtration can afford you to do that. You want to reduce your maintenance and operating costs. You also want to look at, getting the maximum out of your equipment life cycle. And today, again, I keep, harping on risk assessments, but that's a valuable part in everybody's program today. And everybody should be doing that, talking to their chemical provider. There's also a lot of really good consultants out there today that can provide you with a good risk assessment program. Now let's look at some of the equipment that you see out there in the market today. High efficiency filtration. You can see the two photographs. One is a conventional vertical tank design. The other is a horizontal design. And those are a high efficiency system. On cooling water systems, we can rate those 2 sub-micron extraction of suspended solids. We don't put a specific micron size below 1 for the simple fact that all filtration systems, especially sand filtration systems, are nominally rated. They're not absolute. So you can say whatever you want, but measuring that becomes very difficult when you go below 1 micron. There are multiple analysis that you could do. They're very costly. We tend to use laser particle distribution along with the rest of the industry. It's pretty much a common standard, and it gets you in the high 90% probability of efficiency. So you look at that. You look at screen filters. Another great product. But everything has its limit. You have to understand the limit, and the reason why we want you to understand suspended solids. Conduct laser particle distribution analysis. Check with your chemical treatment provider to do that, and they all can do that. So you want to be able to understand what's in your water, so that you know what solutions you have available to you to correct that problem. You also have single and multimedia sand filters. Bag and cartridge filters, cyclone separators, and there's a whole list of others, but these are the most popular. So understand suspended solids, do your testing, and then be able to select what is best for your needs at your facility. let's take a look at traditional sand filters. They are a downflow, plug flow type design. And you're trapping suspended solids from the very top to the very bottom. So as that gets very ripe at the end of its filtration cycle and you have a filter cake on top, you're going to be able to trap submicron particles at that point. But, you know, that's when the filter is at its ripest condition, and then it's going to want to set off the pressure differential to activate a backwash cycle to clean it. And then the process starts all over. Because of the mass balance of fine microscopic particles, they can't really remove, you know, that much of that mass to make a measurable improvement with the water quality. These technologies operate between 4 and 7 GPM per square foot of media surface. If you had 100 GPM filtrate, you're going to need 100 to 150 GPM coming back the other way to backwash with. Typically, you know, when you look at multimedia filters, you know, they need to backwash for 10 to 20 minutes to be able to extract all of the suspended solids that it's trapped from the bottom to the top. So in the HVAC market, it's a very competitive market, and we've seen backwash times reduced as much as 1.5 minutes, and that's nowhere near enough time to be able to properly clean that filter. We've also seen where they'll utilize their filter pump to do the backwash, and when you look at the volume of water that's needed, they'll you know, pipe the system in so that you're using the cooling water or heating water to backwash the filter. Well, first thing is you can't backwash dirt with dirt because you'll eventually over-impact all of the media and it'll start to channel and you have to change it repetitively. So that's characteristics on traditional sand filters. You know, they'll say 5 and 10 micron capability. And yes, at the ripest point of its filtration cycle, you can absolutely say that. But in reality, they're probably a 20, maybe a 30 micron technology. Because understand one thing, clear doesn't mean clean, because the human eye cannot see below 50 micron in size. All right, so when we look at microsand, and in our high efficiency filtration, we have a very close coefficient from grain to grain in that silica sizing. So it's a very tight media. You know, it has a very uniform coefficient, and it does very good as far as the design and microsand with a cross-flow technology. Let's review what cross-flow filtration is. Over 7 years ago, we started a very rigorous R&D program to understand our vortexing sand filter. You know, that's our trade name, Vortisand. And in doing so, we found a lot of CFD, computational fluid dynamic deficiencies, because as you created that agitation in that filter, that fine silica sand, it didn't know, you know, with that topography to keep the level, the depth, equal throughout the entire media surface. So it had deficiencies, had a lot of hot spots. So it was still a great technology, but we were able to redefine it. And when we did our R&D, we discovered that we could create a cross-flow effect by coming in with a different upper injector system. We call it the VortiJet. The whole technology in our filter systems is a patented design. So now what happens is the water comes in, and it's going to either on your vertical tanks, it'll come out a quad head fitting, which is in the very center apex of the filter, very close to the dome of the top of the vessel, and it's further away from the media surface. So now what happens is it comes in, and we use the sidewall on that vertical tank to be able to create this cross-flow sweeping across the microsand on top. We are going to get penetration of suspended solids into the very upper layer of that microsand, but the majority of suspended solids are being held on the surface and up in the freeboard area. So when you have an efficiency of being able to remove down to submicron particles on a single pass, we typically look at 50% or more of the submicron to 2 micron particles, 80% or more of the 2 micron and larger particles on a single pass. But what we miss on one pass, we're going to pick up on subsequent side stream passes through that filter. And that's really the most effective way in side streaming off of a cooling loop. Our sizing requirements are much less because we are such a high efficient filter. We will look at 2 different sizing requirements: 3 to 5% of the circulation flow rate, and also we want to look at turning over the volume of water 7 to 12 times in a 24-hour period. We're going to analyze a lot of things. We have application data sheets that you can fill out. And we'll analyze everything to see what's going to be the best model for your application. The thing that you don't want to do is undersize the filtration if you have a gross amount of suspended solids. You're not going to save resources that way. You're going to waste water because the filter is going to want to backwash more often because it cannot hold the capacity of dirt that's in the cooling water system. So the cross-flow effect is extremely effective in improving a filtration cycle, and yet when we go into a backwash cycle, if we use a 100 GPM filter, we only need 50 GPM coming back the other way, and that's because of the design. We are just fluidizing to release the upper suspended solids from that top layer of sand, and the rest is a cleaning process. And that time sequence can be anywhere from 4 to 8 minutes. It's adjustable in the field with our very smart control package. You know, the other aspect is looking at our our horizontal tank designs, which when you look at 350 GPM capability and larger, we tend to want to offer that horizontal design, because at 350 GPM, we can use a single vessel filter. At 600 GPM, we could use a single vessel filter. At 1100 GPM, we can use a single vessel filter. And still, at those high filtration flow rates, the backwash rate on a model 300 is going to be 75 GPM. On a 600 GPM, it's going to be 150, and on your 1100 GPM filtrate, it will be 300 GPM. So you can see the equation of reduced water use. The other aspect is, you know, we will go to work at going down to that submicron range. As the filter is online and removing suspended solids, then over a very short period of time, typically a 30-day period, you will start to see a major decrease in backwash frequencies. Again, that's water conservation, because the filter, if it's clean, it's not going to have to backwash a lot, but it's keeping and maintaining the cleanest water in your system as best it can. So that differs greatly to the type of other products that are out there. And when you look at, if you look at this chart, element chart, you look down at 0.5 micron, and smaller and higher, you could see where high efficiency filtration is bordering into that microfiltration range. So it really lends itself well to removing all sorts of suspended solids. You get seasonal upsets. You may have a facility where there's a factory down the road, and you just happen to be in the airstream, and that's going to add to the typical amount of suspended solids that enter that system. Comparing traditional sand filters to the cross-flow high efficiency, again, because of its high efficiency and the sizing requirements, you will see that the footprint is greatly reduced. The high efficiency cross-flow design, it operates between 15 and 24 GPM per square foot of media surface, compared to a traditional filter between 4 and 7 GPM. And they can only make the water moderately clean compared to high efficiency. So when you look at all of these things and you try to equate that into a return on investment, these are all the things that we consider, and you should also. You know, the types of applications, you know, in our 30-year tenure, we've done just about everything imaginable globally on water. You know, if it's dirty, you can filter it, but there are limitations, and you have to understand, and we'll help you understand what our limitations are as well. Every technology has them. Just make sure that you do your particle distribution, select the right product that's going to, you know, fit your budget and fit your needs, and be able to do a good job. At HVAC, process cooling, you know, in the manufacturing aspect for processed waters, wastewater, we're pretty good at polishing tertiary wastewater. That's becoming a very popular use for cooling tower makeup today. You know, rather than use potable water, which, you know, we're getting less and less of it. You know, if you read all the reports, you know, we should be, you know, very thirsty. But again, you know, you have to understand there are other things going on to try to save money, to try to save pure water. And these will bring in a new characteristic when it comes to operating your cooling or heating water systems as well. And we don't care if it's a data center or a commercial property or an industrial site. I'd like to look at the case study here. The big challenge they had, and again, it was because they did particle distribution testing, and it showed 95% of all the suspended solids at this airport, they were under 5 micron in size. So that left very few products that could really handle that. And we won this project, you know, and you know, we were able to, in less than 2 years' time, be able to show them over a $300,000 return on their investment with water, sewer, chemical costs, etc. You know, that would go to the drain typically. So, you know, we can share any of this information with any of you. We have case studies in all sorts of applications. This happened to be another really good challenging situation. It was a district energy center that was being plagued by real fine suspended solids. They were using a traditional sand filter, which really wasn't getting out the amount of dirt. So what we did is we installed a vorticant in there, and we were able to reduce their heat exchange cleanings astronomically. But these are the type of things that we do on a daily basis, and we look forward to the opportunity of working with any of you to let you see where you can make those improvements as well. So again, you know, I just want to reiterate, you know, clear doesn't mean clean, and you have to do particle distribution in order to best define what your objectives should be and how you should handle that. And the sub-micron high-efficiency filtration technology, it does matter. It plays a big part in today's operations. You know, all operating costs, they never go down. They always go up. So when you look at your energy costs, your water costs, your sewer costs, your chemical costs, if you're wasting chemicals, you know, get back into where you have to be, and couple a good high-efficiency filtration system with your treatment program, and you'll have a win-win situation. And again, you know, let us help you look at your bottom line and improve that with high-efficiency filtration. So again, you know, we want to thank you, and I'll turn it back over to Vincenzo.
Well, before we conclude and start the Q&A segment of this presentation, just a quick reminder to type your questions into the Q&A panel on the right-hand side of the screen, and be sure to send your questions to all panelists found within the drop-down menu above the text box. On behalf of Vortisan and Local Water Technologies, we thank everyone for attending this morning's webinar. Vortisan is offering a free laser particle count and analysis with an applications engineer subject to their approval. Please include the following information listed on the slide within your email to vortisan@evoco.com, and you'll be contacted by one of our water experts with water sampling procedures and shipping information. In the event you're looking for more information on process cooling, we have included dates of our next webinar. Now we'll be moving forward with the Q&A period with Keith. Okay, so we have a question here. Savings, so Keith, savings appears to be better due to lower pumping head and better heat transfer in the heat exchangers. So when someone states a savings due to this filtration, how much of the savings is from better pumping and how much is from heat transfer?
Well, typically when you're able to reduce the suspended solids, and that creates a biofilm, an insulating barrier. You know, you'll see an average of a 5% energy savings with those cleaner heat transfer surfaces.
All right, the next question. Does a water softener on the makeup water help the system or elevate the need for another filtration system? Is it cost effective on a cooling tower application?
That's a great question. And you have to be very careful with adding soft water into a cooling tower system. It has to be blended at a lower percentage. And what that does is that allows you to cycle up that tower a little more. All right, because the cycles of concentration are based on the hardness minerals coming in from the municipal water supply or whatever the supply is. So what you don't want to do is feed a whole lot of soft water, because that can start a corrosion issue with your entire system. But it is something that is and has been used to help increase cycles of concentration, but it will not negate the need for a filtration system. You still need to have filtration to remove the suspended solids.
Okay, and there are quite a few questions coming in. So for the last question, while we have time, is there a minimum size system in tons where this technology makes sense?
Repeat that again, Vince.
Is there a minimum size system, or I guess you could say requirement, in water volume where this technology would make sense or would not make sense?
Well, when you look at the sizing criteria, you know, and it depends on the size of the cooling tower as well, or your chill loop, because thermal chilled water we size much differently than we do, say, on a commercial property chill water loop, where you look at maybe 1 to 2% side stream flow rate or 1 to 2 turnovers a day, versus the open cooling tower loop, you know, being 3 to 5. You can undersize to a point. And as I said earlier, you don't want to get into the range of being really undersized versus the mass balance of suspended solids that are entering or in the system that will impact the amount of backwash cycles required. If you're continually in backwash, you're not very efficient. I hope that answered your question.
Yeah, and I think we have time for one more. How often do you need to change out the filter media with the Vortisan system?
Another good question. Because we have such a high efficiency in our filtration cycles, the media pretty much stays intact, and you don't lose it through backwash, which is called carryover. So you have channeling when you channel media down, and carryover when you carry it out through a backwash cycle. So we've designed the filter to minimize that to an absolute minimum, and you're not going to you know, impact the design of the filter.
Great answer. Thank you, Keith. Well, that concludes our presentation this morning. For those of you that asked questions and weren't able to attend to them at this moment, we will be calling you and following up with an answer via email and as well as a phone call to clarify the answers and elaborate more. Thank you very much for your time, and have a great day.